Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by CJ.
Hi, I'm CJ. I'm a first-year mathematician in Brazells College.
Brilliant stuff. CJ's on to talk about some maths, which we're going to do in a minute. CJ's done some research on a topic for us today. But first, I thought I'd say hi to people in chat and answer a question quickly. People, before we went live, have been talking about exam boards. I suppose general guidance now is that people are doing their exams, they're getting their marks. They want to know, does their exam board data get sent to Oxford? Does their mark get sent to Oxford? And the answer is, we can see which exam board you did because you declare it. We don't mind which exam board you did. An A star is an A star in maths. We don't mind. And we don't get the raw marks. So they are not shared with us automatically. Yeah, cool. And hi to Kai, and I saw Miles in here and other things around. I don't know what Learning Resource Network A-level is. Cambridge International A-level, I know about that one. That's equivalent to Edexcel or UK A-levels. I'm going to have to look up Learning Resource Network A-level. Right, that's my day job, admissionsy stuff. It's after 5 o'clock, so it should be maths time. Let's check how chat are doing. CJ, I don't know if you've seen us do this before. We always start the live stream by asking how people's day was on a scale from 1 star to 5 star, because our chat feature has the ability to do that. They're currently voting. How's your day on a scale of 1 star to 5 star?
Yeah, it's quite good actually. This morning I started with 2 hours of lectures. Then I came back, grabbed some food, and sort of just in general do my work and my problem sheets too.
Full day of
Yeah,
maths at 2 hours. Also, sounds like a pretty standard first year mathematician day. You've got your lectures in the morning, you've got your thinking about maths in the afternoon.
yeah,
Um,
exactly. I
Pretty
had
good.
my tutorials yesterday and on Tuesday, so I don't really have tutorials this afternoon. But otherwise, in a normal afternoon, I will have tutorials as well.
Okay. Yeah, I had some tutorials this afternoon, the other way round. I did some teaching differential equations, which is always a roller coaster. Good times. I think I'm having a 4 star day. I think. Um, sometimes I think my day is improved by going up and doing um, Oxford Online Maths Club. Let's find out. Kai has learnt about multivariable calculus. CJ, have you learnt about multivariable calculus? You must have by now, right?
Yeah, it's actually a module I'm doing right now, multivariable calculus.
It's a question. It's not a dumb question in chat. It's a question. What's the difference between a tutorial and a lecture? I think it's a good point to explain that. Do you want to explain what the difference between tutorials and lectures is at Oxford?
Yeah, definitely. So for lectures is mainly going through like the course in general, as in there will be lecture notes, of course, and it is expected to sort of read the lecture notes in advance, and the lecturers go through and explain the difficulties on the lecture notes during the 2 hours lectures every morning from Monday to Friday. Whereas for tutorials, it's mainly for you to sort of resolve the problems you have on the topics. So there'll be problem sheets given and assigned, and you're expected to sort of submit them before your tutorials. And on a tutorial, it's mainly going through those problem sheets. And if you have, of course, if you have other questions about the course in general, of course, you can ask your tutors about them.
I'm one of the tutors for one of the courses in one of the colleges at the moment. Those are sort of the Oxford special thing that, as well as having these lectures, which is kind of normal university experience with everyone together, and we do this small group teaching alongside. So something I quite like is meeting my students, finding out how they're finding the course. Let's see, how's this going now? So the poll has come through. I think 5 stars has won for the first time in my memory that 5 stars has won. So chat's having a good day. I'm always looking out for people who have voted 1 star or 2 star. Today, that is no one. Um, this is the best mood that chat's ever been in. Let's make the most of it while we're here. The Jamie's here. Hi, Jamie. Somebody's done a science experiment where they found out that the gravitational acceleration constant is 5, which is not quite the most accurate physics thing I've heard about. Somebody says it's their first time in chat, which is brilliant. Hi to people in chat, which is a reminder that there's always someone whose first time is this episode. Um, welcome to the Maths Club. This is what we do. We just chat about maths. I can't answer that phone call right now. It's still ringing. This is what we do. It's never got any technical problems at all. It's a highly professional live stream with no exploits. I've got 2 adverts on screen. I'm going to read them out really quickly. Then I'm going to let CJ talk about maths. There's the Teddy Rocks essay competition running at the moment. You can enter that if you like and write an essay, or if you just want to read other essays about maths topics, kind of similar to how we just talk about maths, you can visit that link on the St Edmund Hall website to find some other people's maths essays. Please don't plagiarise them for your own maths essay needs. Please don't re-enter them into the same competition. Is this obvious? Please don't ask ChatGPT to write you an essay for the essay competition. All of these things would be bad and immoral. Instead, why not apply for Promise Europe? Or even if you don't want to apply for Promise Europe, there are some problem sheets on the web that they set for applications. The problems are really good. We're not going to talk about them on the stream. And we're not going to talk about them on the stream. Instead, we're going to talk about Zeno's paradox. Is that right? Is Zeno's paradox time? I think it's Zeno's paradox time now. Somebody in chat says that they just phoned me, maybe, which would only be a tiny bit funny. It would be not very funny. I have now muted my phone. Ha ha ha. Okay, CJ, over to you. Zeno's paradox. What's going on there?
Yeah, so there's the old Zeno's paradox, which is the Zeno's arrow paradox. So the philosopher argues that time sort of can be broken down into infinitesimally small sort of chunks of time, and if we assume that an arrow is flying from A to B, then at each instant, at each sort of those small chunk of time, the arrow is moving at an infinitely small, even a negligible amount of distance. So he argues that if we sort of sum up over the time for all the distances that are negligible, the arrow is essentially not moving in this period of time, which is a paradox because the arrow, of course, in the air, it must be moving from A to B. However, in the modern day, of course, with calculus, we're actually able to sort of integrate and sort of actually sum up those infinitesimally small amount of distance traveled to actually get something that's not negligible, which makes a lot more sense now. And yes, so today
should we do a diagram for Zeno's paradox? So this arrow in motion thing. Should we do a diagram? Because I think it's quite a weird concept. Let's give it a go. So if you're interested in philosophy of maths, you might have heard of this before. I'm also trying to let in the chat moderator into VBox. We've got a chat moderator today, another current student who's trying to log into VBox. So that's the other fun thing that's going on right now. Let's have a diagram for Zeno's paradox. We've got a Miro board here, right? Do you want to give that a go? Just for the kind of classical version.
Yeah, of course, yes. So if let's say we have a point, okay, perfect. Point A and point B. And we have an arrow. So if we consider a very sort of, and if we have a time scale and of course a distance scale, this will be the timeline and also probably the the distance traveled. And if we take a very, very, very small amount of time and we consider the distance traveled by the arrow within this period of time, then Zeno essentially argued that the distance traveled in this small time delta t is essentially negligible, which is 0. That's what he argued.
Okay, I've heard this sometimes said that at the moment you observe it, the arrow is at a position. Its position is a real thing. Like, it really means something for the position to be there. But the velocity is not a sort of real concept or something. That when you look at the arrow hanging in that moment of time, there's nothing to distinguish it, what its velocity is at that moment. So it's almost like you can't have a concept of velocity existing at a point. I might be confusing Zeno's paradox with a different paradox actually now that I think about it. I think Zeno might have had multiple paradoxes. I might be
Yeah,
muddying the water.
I think it's a different way of paraphrasing it. Uh, because if essentially because velocity is just distance traveled over a period of time, and since Zeno argued that over this period of time, the distance traveled is negligible, so he argues that from this observer point of view, the arrow is essentially have zero velocity at that position.
Okay, okay. So whenever you observe it, you find it hasn't moved at all. What do people in chat think of this paradox? I think you said that maybe you can solve this with calculus. People in chat, some of them are in A level, some of them are learning calculus. Um, so maybe they already know that they don't quite buy this paradox, or they don't believe in this argument presented by Zeno. I guess it's not really fair pitting Zeno against live stream chat because, well, Zeno's not here to defend themselves, and also they didn't know about calculus. Chat's still talking about retakes. I'm going to leave the retakes and A levels a bit for a while. One person in chat says, I'm confused, which is, I think, a fair response to Zeno's paradox. So what have I got? I've got one short chat message and one longer chat message. Someone's got the half distance argument in chat. I like the half distance argument about running half a race and then running half the remaining thing. There's a suggestion in chat that negligible might not mean actually zero. Is that related to the calculus idea?
Well, yes, definitely, because although the distance traveled is negligible, but however, on a grand scale of things, we're dividing the time scale into a lot of pieces, which means that when we sum over those time scale, then the summation is no longer negligible.
Okay, got it. So the statement is something like, at a small time later, hardly moved. Oh, hardly moved. Therefore, velocity is approximately zero. And I suppose it's this line that people don't really buy, don't really accept this line, that therefore the velocity is about zero. So this is maybe part of Zeno's paradox statement that if you just look at little time, the distance is very small, but hey, the time is also small. So it has moved, it's a small distance, and people in chat know about dividing. It's kind of like saying the area of a square is zero. What's this argument? This is Kai's separate argument. CJ, I'm going to read out Kai's argument from chat. I haven't pre-read it. Kind of like saying the area of a square is zero because an infinite number of lines which have zero area. Yeah, so it's that combination of, I think the combination of infinitely many small things, lots of small things, can they add up to be something? Lots of nothings make a something. And Miles disagrees with the premise that you can divide time into arbitrarily small chunks. I think maybe Miles believes in a smallest amount of time, like, I don't know, half a second or something. Maybe not half a second. Okay, this is Zeno's paradox. Do you know the one about the running half a marathon and then running half the remaining distance? I think it's related.
Yes, I think the version I saw was that if we have sort of this race and we have what is Achilles and a turtle one.
Oh yeah, Achilles
And
in the turtle. I'm gonna draw a turtle.
yes, so basically, again, Zeno argues that by the time that Achilles reached the starting position of the turtle has already sort of moved another like a small distance along the line to its new position, T dash. And then before Achilles tries to catch up to Turtle, it must reach T dash, where at that time again, the turtle will have moved to a different position on the line, which will be, for example, T dash dash. So Zeno therefore argues that Achilles would never catch up to a turtle.
Right, those sort of infinitely many things that Achilles must do on the way to catching the turtles. Maybe you could imagine Achilles distracted by all of these infinitely many tasks to do along the way. Gosh, now I'm thinking of the Trials of Hercules. No, Achilles has got to do a lot of things. So I guess the thematic link between these two paradoxes then is situations where infinitely many tiny things are happening after each other, and this is maybe something that gets drilled into people through calculus and geometric series and limits in some sense. And at university we do loads of stuff with epsilons. I can see an epsilon. No, that's a t, isn't it? I can see a delta, small variables and taking limits. But I think it counts as a paradox in a way, because if you haven't learned lots of calculus and had these ideas driven into you, then this is all a bit weird, and you, I think, can ask questions like, is it actually possible to do infinitely many things? Right, okay. Save the turtles. Yeah, save the turtles. I'm really glad we drew a different picture so that some people try to combine these into a turtle that's outrunning an arrow forever, but I think that's possibly an animal thing. Would a tortoise make more sense because turtles... Right, so we're now talking about turtles in chat. The precise differences between tortoises and turtles. And Miles wants to talk about super tasks, which is a very good YouTube video that's also on this channel somewhere, called Infinity Machines. But I think we're not going into maths and philosophy, if we can avoid it, or super tasks, or Zeno, or Greek philosophy, because I think you wanted to talk about a different sort of paradox, if that's right.
Yes. So right now, this Zeno's paradox is all in sort of like the scale of the world that's in our sort of like day-to-day life. So which means that it's mostly governed by the Newtonian mechanics, or in a sense, the mechanics that are derived by Newton's first, second, and third law. However, there's also another version of this paradox, which is called the quantum Zeno paradox, which is which describes a phenomena at a quantum level, which is no longer sort of related to the normal Newtonian sense of dynamics.
Right, okay, so your plan is we're going to do Zeno paradox, but in a quantum setting. So less archers and Greek philosophers, more Schrödinger and quantumness. Okay. Sounds twice as confusing. Confusing squared.
Yes. Well, so first of all, then the arrow cannot just be, a physical arrow, which is, that long, for example. It will have to be a quantum object, which means that it possesses sort of like very bizarre properties, such as it can all. So if we consider again from the point A and point B, then if this arrow is actually a quantum arrow, then it cannot exist anywhere in between those 2 points. That is first, like, very weird property. And secondly, there can be a superposition of different states, as in the arrow can exist both at point A and at point B, and the probability when we observe the arrow of if whether or not I can find it at point A or point B is given by the Schrodinger's wave equation, which is I think it's psi. Basically, anyway, so the idea is that the absolute value of this wave equation squared is the probability density of the of finding the arrow at this position at this state.
Sure. So people sometimes draw these pictures to show the probability of this thing being in different places. I think the pictures that you see if you just Google it or check Wikipedia kind of look like this for the kind of probability of where the thing is. This is the kind of classic wave, not classic, I should say quantum, the quantum way of saying what the probability of where something is. Evolves, and this shape changes with time. So say, well, I started off knowing where it was, and now I'm not so sure. It could be somewhere else. It could be in these other states. That's the kind of picture that you get when you Google it or when you look on Wikipedia. But I want to stress that for your kind of arrow example, you're imagining that either it's at A or it's at B. It's a sort of two-state system. There's some sort of target at B that we would like to find the arrow at, and either we've hit it or it's still at A, which is, I suppose, some sort of like. Well, do you want to say what? Do you want to say anything about that? A kind of approximation or description of the world?
Yeah, because of course this is very counterintuitive if we use the classical mechanics way of interpreting this event. As in, of course, in the physical world, we cannot have the arrow suddenly going from point A to point B. However, in the quantum world, a lot of things are sort of quantized in a sense that that's where the name actually came from. So we actually allow this to happen.
I see. So the sort of separate idea of quantum mechanics is that things are quantized. So the quantum in quantum mechanics, things are quantized into maybe discrete. I think we first learned about this for energy levels of things, like in chemistry. Things have got energy level. Electrons have got energy levels, and they're discrete and separate, and there's no in between. Either you're in this energy level or you're in that energy level with no in between. Either your arrow's at A or it's at the target at B, with no in between. Okay, so I guess debatable whether arrows work like this, perhaps, but quantum way of looking at the world, discrete quantum states. Cool. Okay, sorry, I really interrupted to draw an irrelevant picture about probability diagrams. Sorry, carry on. Sorry.
Yeah, no worries. And also, another very important concept in the quantum world is the particle wave duality of the quantum object. Well, if we're not observing the object, then it can have wave behavior as shown by the wave equation here. And however, once we actually observe it, we're sort of forcing it into one quantum state. So if we observe it, the arrow is either at point A or at point B. And if we don't, it's at a superposition of the two states. I think it is probable for me to find it at both point A and point B. So this is a very important fact when we're explaining the quantum Zeno effect.
And sorry, just to be clear, because I think I've muddied the water a bit, is that because it's a quantum arrow, or just because that's what we want? I think it's a quantum thing.
Yeah, exactly.
You're saying we're using the whole arrow setup as a theoretical example of a quantum system that's got these discrete states. And maybe it's a bit fanciful for it to be arrows so that we can compare to Zeno's paradox. But I think this live stream might be a bit grim if we said energy levels of the hydrogen atom every time. So I think we should keep saying positions of the arrow. I think it's just more fun.
Yeah, of course.
So kind of it's a quantum fact. We're trying to explain a quantum thing, but also we would like to use the word arrow and position wherever we can, rather than energy levels of the hydrogen atom every time. Good.
Well, yeah, a very similar analogy and a very famous one is the Schrödinger's cat, of course.
Right.
Where basically it's a similar analogy as if we don't open a box, the cat is either dead or alive at the superposition of two states. But when we actually open the box and observe it, we're forcing the cat to be at one state.
Right.
So it's sort of the same analogy here.
Sure, and of course real cats have lots of states like happy and sleeping, but the cat in Schrodinger's cat box model thing it's kind of playing a role as a kind of analogy or metaphor, I suppose, for something that's got two discrete states. Surprising fact, some things have discrete states. Right, okay. I've really taken people off track. Okay, quantum arrow in one of two states. There's some Schrödinger equation that describes how that probability changes over time. Okay, so I guess either there's some probability that's in state A and some probability in state B.
Yes. Well, so if we assume that we start with state A, if we sort of start observing it at state A, so we have a very, very high probability of seeing it at state A, which means we sort of have this like spike in the wave function
Hmm.
because we're sort of observing it, which means that we're sort of forcing it as state A. Then over time, we'll sort of have this sort of continuous wave function because we're no longer observing it. So the wave function starts to evolve. So we'll have a lower probability at A and also probability at point B as well. So if we observe it at this time, we can either find it at point A or find it at point B, and the probability of finding it depends on the sort of the amplitude of the wave function in a sense.
Okay, so
And,
over time, while we're not looking, and I'm avoiding the separate tangent about what it means to be looking at the arrow, while it's not being observed, whatever that means for hydrogen atoms, and while it's not being observed, the probabilities change over time. So you've drawn this one coming down and that one going up. So there's some probability that we find it at B, and then we observe it, whatever that means.
and
And yeah, sure. Okay.
yeah,
Yeah.
and yeah, and then eventually, when we observe it, we'll sort of would most likely to find it at point B. So this is sort of like the end stage of the quantum in this system, basically.
Okay. So there's some. Sure. Okay. The system evolves until after some time. If we wait a while and then observe, then it's probably in state B. There's some higher probability. Okay, cool. This is a kind of strange way to do an archery competition, I suppose. They fire the arrow. We don't look. Nobody looks. And then we wait an amount of time. And if you wait a short amount of time, it's probably still at A. But if you wait a longer amount of time, it's probably at B. I suppose that almost works as a description of normal archery competitions. It's just a really weird way of judging it. If you wait after a long time. If you've just joined, you've missed the statement of the old Greek philosopher Zeno's paradox, and we're now trying to explain quantum mechanics so that we can do quantum Zeno, which is a paradox and quantum mechanics at the same time. Okay, my archery competition starts. If I look straight away, it's probably they're about to fire the arrow. If I look in an hour or something, then probably the arrow's at B. In between, I'm not sure. For quantum reasons, the arrow is being forced to either be at A or B. So when I observe, when I look, I'll either see the arrow still at A or I'll see the arrow at B. So the quantization of forcing it to be one place or the other means that when I observe it, I'll see an outcome. It'll either be at A or B because of discrete positions. Okay. So what's the paradox? It's weird, but what's the paradox?
And well, so in the first case, where we sort of wait a very, very long time to observe it, then the wave function most certainly evolve into this state, which means that we'll see the arrow at B. However, if we sort of shoot out the arrow and immediately observe it, then the wave function will not have that much time to evolve, which means that there will still be a very high probability of finding the arrow at A. Because, for example, this is if this is sorry, if this is after, let's say, 30 seconds, but if we observe it after 1 second, maybe we'll find that at point A, I'll use a different color. At point A, we still have this amount of probability, and at point B, we'll only have a tiny bit of probability. So if we observe after, let's say, 1 second, it is very likely that the arrow is still at the starting position A. And if we observe it, then the wave function will go back to sort of this starting position where the probability of finding the arrow at A is 1, which is definitely. So this one means that, well, the wave function has to evolve from the start again into this state.
Right, I'm judging the archery competition. I'm not looking, but then I look and I see that they haven't fired the arrow yet. And I say, okay, right, when you're ready, and I close my eyes again, and that's like starting the competition again. They haven't fired the arrow yet, but it's at A. and there was some weird quantum stuff going on when I had my eyes shut. That meant it could have been at B, but I looked and it's at A, and that's like starting again.
Yeah.
Okay. So I guess the idea is if I look very frequently, what happens?
Well, if we look at it very, very frequently or frequently enough, then we are continuously changing and forcing the arrow to be at position A. Because before the wave equation can evolve far enough such that we can find the arrow at point B, we're stopping it by observing it, and then sort of once we observe it, we're forcing it back to the original state, i.e., time equals to zero. So if we're frequently, very frequently taking observation at a very short period of time, then we're essentially freezing the arrow at point A.
Yeah, which is weird. So if I keep looking at it, if I keep observing it lots of times, then it will stay at A, even after a long total amount of time. It reminds me of the game. There's this kids game in the playground. I don't know if you've ever played this. It's called Grandma's Footsteps, I think, or What's the Time, Mr. Wolf, or something. Is that something you've done, or?
Not really.
I'll describe it, and we'll see if it's got global appeal. We've got an international audience watching, so I'm now forced to describe a possibly very local, regional kids game. Someone in chat will help me out. So there's this kids game. You have a group of people, and one child is some distance away, looking away, and the other kids have to quietly sneak up on that child, who at any point can spin around, and if they see you moving, you're out. So you have to try and sneak up on this person very quietly, without making enough noise that they spin around and observe you, and then you're out. People remember this, but people in chat seem to think it might be a British classic. Of course, if you think it's a British classic, that's probably because you're British, so you wouldn't know if it was, or maybe who knows? Who knows? People always turn around. Yeah, they can't move when you're being looked at. Can't move when you're looked at. Okay. The exploit for this game. CJ, am I making any sense? Is this a thing?
This is exactly a thing, yes.
Right. What's this called?
Uh, I think in China it's called sort of 1, 2, 3, sort of like wood or like
Wood.
wooden. Yeah, because you're supposed to be still as a wood.
Oh right. Okay.
So you're not supposed to move, or else you will need to go back all the
Wait,
way.
is the counting how long before the person spins round, or is it like a
No,
warning? No. Okay.
yeah.
What's the time, Mr. Shark? Says somebody in chat. So that's like an updated version. What's the time, Mr. Wolf? I guess the counting. Cool. Well, I'm glad that's a thing in other places as well. The chat seems to be quite famous. Oh, their name's got a fox in it. This feels like still fashionable with the teens, says somebody. So, you know, and somebody else is just reacting to Mr. Shark as a concept. I think we may have invented something. This is how it gets global attention. Right, okay. So in the popular childhood game, What's the Time, Mr. Shark? The exploit for the kid who's being caught is that they can spin round really frequently. If they look really frequently, then nobody's allowed to move. Which is a bit like Zeno's paradox, because when they look, there's no velocity, nobody's moving. Everyone's still as it would. But so if they observe really frequently, then they can force everyone to not really have time to move, which in a physical sense sort of doesn't work, sort of doesn't make sense in the kind of Newtonian physics way, right? Because they could move a small amount in between your observations. But in a quantum sense, it turns out that this strategy does work, and it forces them to stay at the start point. Are we talking about that one Mario Party minigame? I guess we are. What's the time, Mr. Shark? I'm really leaning into this metaphor. This is brilliant. Because when the kid's looking the other way, right? They don't know where the people are. that uncertainty is a little bit quantum. There's some probability that the person is at the start point, and some probability that they're about to get got.
Yeah,
Um,
exactly. So
yeah,
basically, we're assuming that the kids can run very, very fast,
I
as
suppose.
in
Yeah.
the probability that they can run very, very fast and reach me at this very small amount of time.
Well, I suppose there's maybe another version where instead of just having two states, start position and end position, we have like a hopscotch grid or something, and there's some different states that they could be in. But I can still freeze them at the start square by observing them frequently in the quantum sense. Um,
Yep.
Statues, also known as in different regions of the world. That sounds like the Wikipedia link for us. Right. Okay. I'm learning about red light, green light redirects here. Oh my goodness. Right. Okay. Right. For people watching all around the world, there's a link in chat to the Wikipedia list for you to do a look up for whether this is the same game that you remember as a child. Um, okay. So
Um,
Newtonian sense, the strategy doesn't work. Quantum sense, you can freeze people at the origin.
yeah,
Hmm.
and also just when we talked about the different states, I guess it sort of works similarly for an atom, as in the electrons have different energy levels. So in that sort of system, the electrons can be at different states instead of at two states only.
Hmm. Hmm. Right. So there's discrete jumping. That's an example of something where this discrete thing makes a little bit more sense.
Yeah.
Um, Um, Miles wants to know if it eventually ends up at B due to the small probabilities, which is a bit like asking about the calculus approach to the original Zeno's paradox thing. There's lots of small things. Maybe those small things add up to a big thing. Kind of using the same sort of argument. Um, Somebody anonymous says, "Very good question, Miles." I'm sure it's not Miles again, but it's funny to imagine that it could be. Are you turning around instantly? You're turning around at some high frequency. Um, the faster you spin, the more likely they are to stay at the origin. Let's do some maths. Shall I do my quadratic thing? Do you want to do something else before I do the quadratic thing? Because the quadratic thing's a bit
Well,
complicated. I feel like we should, if we're going to lose people with the quadratic thing, we should say the interesting thing first. Do you want to say anything more about quantum Zeno?
well, it's not exactly very interesting, but just that it is actually sort of proven empirically, as in, so scientists actually shine laser beams on ions such that uh, so all the ions for all the ions, the electrons are starting at state one, the very ground state,
Mm-hmm.
and if they're at state one, if they absorb the energy from the laser, they release photon. But over time, if nobody observes them, they will all of the electrons will evolve to state two, and at state two, once they absorb laser beams, they will not release photons. So in this experiment, the scientists actually shine the laser beam at a very high frequency at the bunch of ions, which and the result is that they constantly release photons, which means that all the electrons are sort of frozen, their states are frozen at state one and cannot evolve to state two.
So you can actually do an experiment exploiting not arrows and targets, but exploiting electron energy levels. To be clear, I'm not suggesting that Miles is cheating. It's just immediately where my head went. Sorry, Miles. Um, I think it was because the message ended with the word Miles, which is also how Miles signs off messages. Um, yeah, we'll make the open day really awkward, Kai, if everybody turns out to be a chatbot. That'll really fall through. Um, Somebody in chat, I think anonymous, asks what you're studying at university, CJ, and does quantum mechanics come into it? I can't really tell what they're thinking when they ask this question. Like, are they really scared of quantum as a concept, or do they want to
Uh,
learn more on a maths degree?
I think for the first I mean first year right now, and all the modules I take are compulsory, and for the first year it's like it's like half of them are pure courses, and half of them are applied courses. And I think quantum mechanics is a topic for second year mathematicians. But I think it's optional, so you can choose to take the topic if you're interested.
Yeah. Okay, so not yet in the maths course because you're first year doing maths, um, but at some point you do get to do some quantum maths. There is a surprising amount of maths, including lots of linear algebra, matrix theory stuff in quantum mechanics. Um, I saw someone in chat. It went past really quickly, but someone in chat said something about Doctor Who, which reminded me that you put something about Doctor Who in the research notes.
Oh yes, yes, actually. So I remember in one of the episodes there's a creature called the Weeping Angel, which moves extremely fast. So we can approximate it as a quantum object moving from A to B. So Doctor Who sort of warns his friend to not blink or look away when facing the Weeping Angel, such that they can actually freeze the movement of the Weeping Angel, because uh, it is a quantum object in that sense.
Right. Okay. It's either got you or it hasn't. Yeah. Classic. I love that you say it's in one episode. It's like sort of some like a really strongly held opinion. Like Matrix is a really good movie. Too bad they never made any sequels. Um, oh, has it got a citation on the Wikipedia article as well? The Weeping Angel's secretly a bit like the statues game that we played as kids. Okay, right. Well, we're learning a lot. Um, there's also a question in chat about A levels. Did you do A levels or something like that?
I did IB
Right.
and
Okay.
higher level math analysis and approach.
Cool. um, just wink instead. I think what we're saying is, if the angels are quantum, then as long as you unblink really frequently, then you'll be okay. Shall I do the quadratic thing? I kind of feel that I've overhyped the quadratic thing. It's really confusing. Okay, so I want to try and answer the question about does doing lots of small things add up to a big thing? Like we were worried for the original Zeno's paradox that the arrow moves a tiny bit in between moments of time, but overall that adds up to it moving straight from A to B. In a quantum sense, so we're going to skip all the quantum mechanics, but I'm going to do the thing. So you start in state A. Oh my goodness, I can do this. Start in state A, and then some quantum mechanics means that at later time t, the probability that you're at A at time t is roughly 1 minus alpha t squared, where this is roughly for sort of small time, whatever that means. And this alpha is all sorts of stuff to do with h bar, which I'm really not going to do. But there's some sort of number here for how that probability changes, so that at time t, okay. And I'm afraid for the live stream today, we're going to need to take this on trust. Have you seen this fact before, CJ?
Yes, a bit. And I believe it's 1 minus alpha t squared. I think it has something to do with the Taylor expansion or the Maclaurin expansion. And
Yeah.
we can ignore the higher order terms because the time is so small.
Yeah, there is a Taylor series in there. The Taylor series is kind of the friendliest bit of the calculation. The problem is that the calculation kind of involves exponentials of matrices, and it also involves complex conjugates. And the chance that I can get through the matrices, vectors, complex numbers, conjugates, and exponentials of that's H and matrix, while also explaining what H bar is. Oh my goodness, we're just not gonna do all of it. It's some number alpha. It's a bit like a cosine. I don't think this has explained the quadratic thing yet. No, I don't think I've explained the quadratic that thing yet either. I've also not been looking at chat recently. Yeah, moving between nodes discretely. It's a bit like graph theory. Yeah, I suppose if you have lots of nodes, you could imagine that being forming a graph. I guess a kind of a complete graph with some probabilities of transition between them. What is the quadratic thing? Here we go. Okay, so let's say after t, that's probability. If I have some slightly bigger time t, this is not really a statement, I suppose. Fine, okay, that's the probability. It's a bit less than 1. Instead, if you split that up into n observations, at times kt over n, so this is splitting up that time big T into individual observations, n of them, and I'd like to split that at 1 times t over n, 2 times t over n, 3 times t over n. This is your plan to look at the weeping angel quite frequently, or you're a child playing statues and you want to spin around really fast looking at, I'm imagining spinning all the way around really fast, it's a constant lighthouse of observations. Then, oh my goodness, so let's do this. So the probability that we're still at A after all that, I need to write slower. My whiteboard is not keeping up with the excitement I have for this content. So here's the probability that we're still at A after 1 observation. I put in the time after 1 observation. After that, between the first observation and the second observation, the thing resets. So the first one is, I've seen it, it's now at A. It's at A and it starts again. This is the thing you said about it starting again at A. So in order to stay at N, it's stay at A after N of these, it's got to survive N, this N times. After all of that, the probability of being still at A is about 1 minus alpha big T over big N squared, all to the power of N. It's kind of a probability tree in there, I guess, right? Like either it's there or it isn't, and then if it went to B, I guess maybe it could come back again to A, but that's quite unlikely. And it's quite unlikely it went there in the first place. So it's roughly this probability for large N. That's approximately 1. So it's not the case that that goes to something else, that like some non-zero probability of transition. For large N, that just tends to the number 1. It works out. You could binomial expand it if you wanted to. I think I'd recommend not binomial. N's an integer, go for it. Sure, binomial expand it. Yeah, so if you binomial expand it, all of the terms, other than the first one, all of the terms have n's in the denominator. So if you do the binomial expansion, all the terms have n's in the denominator, they all go to 0, and you're just left with 1. There's no interesting term for this probability. Is Euler's number in here? Chat thinks that Euler's number's in here. I'm not so sure. CJ, sorry to do the quadratic thing, really. Really took over your live stream, sorry.
It might be because it looks something similar to the compound interest formula.
Oh, yeah. Well, okay, so there's something useful to say here. What's that? How does that work? That's like
From what I remember, so E is equals to
it's the limit of something, right?
yeah, limit of as n approaches infinity of 1 minus 1 over n to the power of n.
Very good. Yep. True fact, I think. That's E 2.71828182845904552. Pretty good stuff. But this one, crucially, this one's got an n squared down here. So it's boring. It just goes to 1 instead of going to E. I guess I'm glad it doesn't go to. Oh, is this e to the minus one? I think this might be e to the minus one.
Yeah, yeah, sorry.
That's right. With a plus sign, I think you get e. With a minus sign,
Yeah.
I think you get 1 over e. Yeah, so that's kind of what I expected, I suppose, that after time big T, there would just be some number like 1 over e for the probability it's at a now. It's like, probably not. It could depend on big T, I guess, and as big T grows, it would decrease. I was expecting, I suppose, something like e to the minus alpha t. I don't know. I guess it's some of these approximations stop working at some point, but it's actually something like this, that it tends to 0 for large t or something. But that's not true at all. It tends to 1 for large n. There's too many limits going on at the same time. Yeah, it's not quite any expansion. I think I'm slightly behind reading chat, but because this is t squared over n squared down here, the thing inside the brackets is getting really small, really fast for large n, which means that this is actually getting close to 1. Let's do the binomial expansion because it was a good suggestion in chat. I don't know what I'm doing. I don't know why I've agreed to do the binomial expansion. How did I talk myself into this? I regret everything. CJ, tell me something about birds. Is there something about birds and Zeno's effect?
Oh yeah.
We did some research before the stream and we found some maybe applications of this.
Yes. It's a bit weird though, because uh sorry. Yes. So there's a thing about birds that they have the something called magnetoreception, which means that they sort of can see, in a sense, see the magnetic field of the Earth. So that's how they sort of, for example, migrate from one place to another. So one paper actually suggests that the quantum Zeno effect is a key mechanism in the bird's magnetoreception function, basically.
Crikey, okay. So there's combining there Greek philosophy, quantum mechanics, biology, and electromagnetism. So, it's probably a nice simple paper that we can all put in the further reading and just understand really quickly. Obviously not. It's always nice to know that like modern science is so far ahead of where I might have guessed, right? That the things people are working on are just... The world's amazing, right? Someone told me once, and I think this might not be true, but I'm going to repeat it anyway, that if our eyes were slightly better, we would be able to detect individual photons. I don't know if that's true. Someone in chat will tell me that's nonsense, but light's arriving in discrete photon bumps. If your eyesight was a bit better, not stupidly better, but a bit better, like a factor of 10 better, then in low light levels you would notice that low light is spotty or on off. No, maybe.
I actually haven't heard of it.
Never heard of that, doesn't sound true. Why am I drawing a Spinski triangle? Drawing a Spinski triangle because somebody in chat said that I bring everything back to Pascal's triangle, and that reminded me that I am bringing this series back to Pascal's triangle. The very first episode was about Pascal's triangle, and then accidentally the second episode was about Pascal's triangle as well. It just turned up. And then the third episode also mentioned Pascal's triangle, and then we tried our best not to talk about Pascal's triangle since then. But for the last episode of this season, I'm going back to Pascal's triangle. We have unfinished business with Pascal's triangle. If you colour in the even numbers in Pascal's triangle, or I suppose colour in the odd numbers of Pascal's triangle, you get a lovely Sierpinski triangle pattern, lovely sort of fractal comes out. If you colour in the multiples of 3, you get a lovely Sierpinski triangle. If you colour in the multiples of 4, you get something else, you get something different. And if you colour in the multiples of 5, it's fine. So we've got this kind of unfinished business about what's going on there. Why is it sometimes a nice Sierpinski gasket kind of thing, and why is it sometimes a more complicated mess? Did you know that before about Pascal's triangle?
No, it's something new to me as well.
Hey, colouring in Pascal's triangle.
It does sound fun though.
There you go. Colour in the odd numbers in Pascal's triangle. It's really good. The episode was really good fun because at the start we asked what people's favourite triangle was, and some people said Pascal's triangle, some people said Sierpinski's triangle, and then we got to satisfy both of those people by finding Sierpinski's triangle within Pascal's triangle. Sometimes I see spots if the light is dim, but I seriously doubt I'm seeing individual photons. Okay. I'm going to put optical physics on the list of things that I am not qualified to comment on. That's that. Have we got any questions from chat? I think if we say anything more about Quantum Xeno, we're going to make it worse. I don't know. Is there anything else we should say about Quantum Xeno? We'll put stuff in the further reading, I guess. Not sure. CJ, anything else for this before we try and take questions from the audience?
No, I don't think I have much to add.
Yeah. Somebody's called me autistic for... No, they're not calling me autistic. They're saying that if your brain should filter that out unless the individual is neurodivergent. So it's a little bit close. Good. There's a question about promise that I think I saw whiz by before by Arjun. Do you know how many of the questions you'd be able to solve to be a competitive applicant? I've got no idea, Arjun. I think that even if you don't solve a problem, if you engage with it and you try out the question and you do things with the question, that's still interesting. So this is a summer camp where they set some maths questions beforehand to decide who's going on the summer camp. They encourage you, in the instructions there, they encourage you to talk about what you were thinking and to explain your answers, and if you've made partial progress, to explain partial stuff. So I don't think they just tick, cross and count how many you did. Further reading is available when we do further reading. It's available on our website, which is math.ox.ac.uk/r/club for the Oxford Online Maths Club. When we remember and when we've got time, we put together some further reading notes for people to find out more about the topics on the stream. It's also where you can find our back episodes of about 50 of these Oxford Online Maths Club episodes. This has been a really good one. And I think we're going to wrap up in a second. I'm just giving chat a moment to catch up. Somebody says they don't see spots in dim light. They see blue arcs. And there's a request for fractals in chat at some point. Is it too late to start the Promise application? I don't know. I don't think it's too late to download the PDF of problems and have a look at the problems. And the problems are really neat. So if you download them, then you're allowed to keep them. They don't make you give them back, so it's not too late to claim a copy of the problems now and then decide if you feel like applying. And a question, can you make an Oxford Online Math Club into a DVD? And is that DVD going to be region locked? And more requests for fractals. I think it'd have to be some sort of global release, right? We're currently trying to do a global release, so we'd have to do, maybe there'll be some DVD bonus content of just all of the actual Pascal's Triangle content that I haven't been doing on the live stream for the last 8 weeks. People in chat say thank you to CJ. So say thanks, CJ. Thanks to the researcher this week, who was CJ. The presenter this week was CJ. Chat was moderated by Zachary. I've been James. We'll see you again for another episode of the Oxford Online Maths Club in about 167 hours. Take care. Have a good evening. Have a good week. Bye, everyone.
Bye.
And I'm always really bad at turning it off. Give me a second. How do I... this one. Bam.